Okay, so good day, everyone. So let's now proceed to our next topic, which is the analysis of doubly reinforced beams using again the transform area method. So last time we already discussed the singly reinforced beam. Okay, so now let's proceed to doubly reinforced beam. So for doubly reinforced beam, so this is what we call this one, a analysis. Now analysis that is uh, one that has compression steel as well as tensile steel. Okay, so meaning I already introduced that one last time. No, so it has a beam. We have a beam here, then we have this uh, compression part, and we have this tensile steel. No, say for example, we consider positive moment, so this part here will be compression and this part here will be tension. Okay, so compression steel is generally thought to be uneconomical, but occasionally its use is quite advantageous. No, so economical since you're adding additional bars. No, but there are a lot of advantages in using compression steel. No, so one of the advantages, it permits the use of appreciably small beams that than those that make use of tensile steel only. Okay, so that is one of the advantage. The width, now the width and the height of the beam would be lesser. Okay, so therefore you have smaller beams. Also, it reduces the size, that can be very important for space purposes or architectural requirements that limit the size of beams. Also, compression steel is quite helpful in reducing long-term deflections, and such steel is useful for positioning uh, stirrups for or shear reinforcing, which will be subjected to discussion in the next chapters. Okay, or meaning, so if you have the beam, so if you have this beam here, guys, then you have the bars. Then if you have that compression bars, then that would be uh, helpful in positioning your stirrups. Okay, so that is one of the advantage of using compression bars. Okay, so so these are the procedures in analysis for doubly reinforced beam. So first one is to reduce the tension steel bars with an equivalent area of fictitious concrete, NAS. No, we already know the NAS, so that is for the tension steel bars. Then for the compression steel bars, we uh, will be equating that area to a fictitious concrete area, which is equal to 2n minus 1 times AS prime. Okay, so let me draw this one here. So if you have a beam, okay, if you have a beam here, okay, so this is your compression steel bar and this is your tension steel bar. Okay, then this will be your B, or the width of the beam. Then you have the overall height H. No, then this distance here from the compression extreme fiber to the compression steel bar, this is D prime, and from the compression uh, extreme fiber to the tension steel bar, that is your D distance. Okay, again this is subject to positive moment. Okay, so meaning this is in compression here and this part here will be in tension. Okay, so this is your AS here, AS prime, and this one is your AS. Okay, so how to transform that one? So say for example, this is your assume NA, assume neutral axis, then you have this beam here, or the concrete. So this is the concrete part now. Then what happened here is that you will have a fictitious concrete area here for your tension steel bar as your NAS. Okay, then you also have the this bar here. Okay, so this bar here for the compression steel bar. Okay, compression steel bar as your 2n minus 1 times AS prime. Okay, then you will have this distance. This is your x distance here. Okay, this is your x distance. So meaning if this is d prime, that is d prime, therefore from the neutral axis to the bar, your distance there is x minus d prime. Okay, then then this distance here from the neutral axis to the tension or tensile steel, so this is your d minus x. Okay, so this is the transform beam section. Okay, so for the doubly reinforced beam. Okay, so going back to the procedure. Okay, so why is it that we have this 2n minus 1 times AS prime for the compression steel bar? Okay, so the reason for this is that the crepe or the plastic flow of concrete should the steel bar of the beam be reinforced, so that the long-term stresses in that reinforcing will be greatly affected by the crepe of the concrete. Okay, so as time goes by, the compression concrete will compact more tightly, leaving the reinforcing bars to carry more and more of the load. Okay, so that's why as a consequence of this crepe in the concrete, the stresses in the compression bars computed by the transform area method are assumed to double. Okay, assumed to double as time goes by. In the transform area of the compression bar is assumed to equal to n times their area AS prime. Okay, so the reason for this is the long term crepe. Okay, so to summarize that one, or for short understanding, okay, so that it doubles the stress in the compression bar, since as time goes by, when crepe will occur, then the concrete will start to loosen some of the strengths, and it allows the compression steel bar to carry more of the load. Okay, so that is the reason why is it that there's 2n there, then minus AS prime. Technically guys, that is 2n AS prime. Then we have to subtract it with the holes, area of holes. This is area of holes, because area of the holes is not a part of the fictitious concrete area. Okay, so this is not part of the fictitious concrete area, so meaning this is a subject to a hair splitting, or meaning very small detail should be followed. Okay, so factoring it out, 2n minus 1, then as prime. Okay, so that is for step 1. For step 2, locate the neutral axis, which is assumed to be located at distance x by equating the first moment of tensile area to the compression area of the beam cross section about the neutral axis. So I think this is almost the same with the singly reinforced beam. So equating the two, equating the first moment of the tensile and the compression area. The only difference there is that in the compression area, there would be an addition of the compression steel or the fictitious concrete area, which is equal to 2n minus 1 times as prime. Okay. For step 3, we are tasked to calculate ICR, which is the moment of inertia of the transformed section. Then compute the stresses in the concrete and steel using flexure formula. Okay, so we have 3 flexure formula now, which is for the compressive concrete, for the tensile steel, and with the addition of compressive steel. Okay, so take note, guys, that this y variable there, they have different values. Okay, so you will know later, as we solve the problem, as we solve the problem 2.6, problem 2.6. So we are tasked to calculate the bending stresses in the rectangular beam section given the following properties: n is equal to 10, m is 160, then b is equal to 350 mm, then h 500 mm, then d is 135, d prime 65, as is we have 4 28 mm diameter bar at the tension side, then we have a as prime, which is 2 28 mm bars. Okay, so let me solve problem 2.6. Okay, so now we have problem 2.6 example. Okay, so example 2.6. So let me draw the figure. So we have so we have B, which is equal to 350 mm. Okay, then we have H, which is 500 mm. Okay, so we have 500 mm, 500 mm. Then we have the bars. We have put the bars here. Okay, so we have these bars and this bar here. This is compression bar, which is 28 mm. Then we have tensile, which is 28 mm. Okay, so we have d prime, which is 65 mm. And then we have d, which is 435 mm. Okay, so I think the detail is now good, and n also, guys, don't forget n given, which is 10. Then we have the applied moment, which is 160 kilonewton meter. Okay, so this is the beam section, the original beam section. So now let us transform it. Let's transform the beam. Okay, so let us assume that this is the neutral axis. Okay, so we have this neutral axis here. Okay, so this is now the concrete, now the remaining concrete. Then also the compression steel bar. Okay, the compression steel bar, let me draw this one as blue. Okay, the compression steel bar. Then also the tensile steel. Okay, tensile steel. Then from the compression extreme fiber to the neutral axis, so we have this x distance. Then from the neutral axis to the tensile steel, this is d minus x, it's d minus x. Then take note that this one here is 2n minus 1 times as prime, and this is still nas. Okay, so this is now your transform area or transform beam section. Okay, so let me compute first the values of 2n. Okay, so 2n minus 1 as prime. Okay, so we have this okay, so 2n minus 1 as prime is equal to 2, then given n, which is equal to 10. Then we have minus, okay, so minus 1, then as, take note that our as is 28 mm, so meaning this is 2 times pi over 4 d squared. Okay, so therefore 2n minus 1 as prime is equal to 23,398.58 mm squared. Okay, so that is for 2n minus 1 as prime. How about for nas? Okay, so nas is equal to n, then times, we have 4, I think we have 428 mm. Okay, so we have 4. Okay, so we have 4, then pi over 4 d squared. Okay, therefore nas is equal to I think this is 24,620 or 630.09 mm squared. Okay, so that is for our na is. Okay, so I hope it's clear already, for the values of the fictitious concrete area for the compression steel and for the tensile steel. Okay, next is to locate x, or to find the value of x. So locate, okay, so need to locate x. So again, this is to equate the first moment of the compression and tension area or tensile area. Okay, so first is for the compression area is equal to 350 times x, then times x over 2. Okay, so this is for the take note, this is for the compression or the concrete. So this is 350 mm, then times x, no, that green one there. Okay, so for the concrete, then we have plus. Okay, so we have plus for the compression steel, which is 23,398.58. Okay, this one here, this one guys, no, this one. Then the distance is the for this one, distance is this one here from the neutral axis to the compression steel bar, that is x minus d prime. Now since this is d prime, okay, so x, then x minus d prime is 65, no, 65 minus 65. Okay, so that is for the compression area. Then equate that to the tensile area, which is the NAS, this one here, now, which is 24,630.09, then times the distance from the neutral axis to the tension steel, which is d minus x, wherein d is equal to 435 minus x. Okay, so try to calculate the equation. So I hope we had the answer of x, which is equal to 160.68 mm. Okay, for the value of x. Then now solve for ICR. Now solve for ICR. So for ICR, so we have ICR is equal to, again, let us get the moment of inertia of the concrete on the compression part. Again, this part here, okay, this portion here. Okay, so that is rectangular, and that is BH, which is the value of x, 160.68 cube over 3. Okay, that is for the concrete. Then plus for the compression bar, which is the AD squared, no, the AD squared, or this one here. This is our area, that is 23,398.58. Then our d distance is the x minus d prime, which is 160.68, then minus 65 squared. Okay, so that is for the compression steel bar. And lastly is for the tensile steel bar, which is the NAS, again this one, the AS, which is 24,630.09. then the d squared there is the d minus x, so the d, which is 435 minus x, which is 160.68 squared. Okay, so I hope it's clear already. So again, recall guys the formula that I mentioned last time now about ICR, that is summation of yung IX plus AD squared. Okay, so this is applicable no doon sa for the concrete on the compression part, and this is the area D squared, so this is area D squared na, because it doesn't have any IX na. The same with the tensile steel na, that is AD squared. Okay, so ICR, okay, so ICR is equal to 2.55 times 10 raised to 9 mm raised to 4. Okay, so that is for our ICR. And for the last step, so we are tasked to calculate the stresses, no, the bending stresses. So we will compute the bending stresses for the concrete, for the compression steel bar, and for the tensile steel bar. Okay, so for the stresses, okay, so for the bending stresses, okay, so for the bending stresses, so for FC, so this is for the concrete guys. So again, we have the same formula, which is FC is equal to my over ICR. So we have a moment which is 160 given, then times 10 raised to 6, again convert it into Newton mm, then the value of y here. Okay, so as I mentioned earlier, from the formula, okay, so from the formula they have different values of y. Okay, so the y here is the value of x, right? So this is the value of x for the concrete. So the this one, now this is a neutral axis, then you have this x distance there, no, neutral axis, then the entire concrete. Then for the tensile, you have this tensile here, so the value of y here, no, this is x, and the value of y here is d minus x. Okay, this one here, d minus x, if this is d distance. Okay, then for the compression steel, this is your compression steel, then this is d prime, then the value of y here is x minus d prime. Okay, so this is x minus d prime. Okay, so I hope the values for y is already clear now with regards to the illustration. Okay, so going back to the whiteboard, so m, then y here is x now, so since this is concrete, so we have 160.68, then over 2.55 times 10 raised to 9. So therefore FC is equal to I think this is 10, not 10.08 MPa. Okay, so bending stress for concrete. Then next is for Fs, this is for the tensile steel. So Fs, again Fs over N is equal to My, right? So we have My, then ICR. Okay, wherein M is equal to 160 times 10 raised to 6, then Y is as denoted earlier, this is d minus x, and d is equal to 435 minus 160.68, then over 2.55 times 10 raised to 9. Then do not forget to multiply the modular ratio, which is 10. Okay, so therefore Fs, bending stress for tensile steel, is equal to 172.12 MPa. Okay, so again for the tensile steel. And lastly, okay, so lastly for the Fs prime. Okay, so formula there is Fs prime over 2n, okay, over 2n is equal to m my over ICR. Okay, so let us verify from the handout. Okay, so 2n, so that is the only varying variable there, for tensile and compressive steel. Also the Fs, will denote as Fs prime. Okay, so we have m 160 times 10 raised to 6, then times y. Again, the value of y here is x minus d prime. Okay, wherein x is 160.68, then minus 65 the d prime, then over 2.55 times 10 raised to 9. Then do not forget to multiply 2n, is 2 times 10. Okay, therefore Fs prime is equal to 120.07 MPa. Okay, so that is for the bending stresses for the concrete and steel bars involved in the doubly reinforced beam using transform area method. Okay, so I hope everything is clear, and we are done with chapter 2. So by then we will be discussing the chapter 3, which is the ultimate strength design for beams already. Okay, so we will be discussing there the codes, the design codes for 2001 and 2010 in designing the beams, using ultimate strength design. Okay, so thank you guys for listening, and keep safe, everyone.